Okay, so good afternoon, everyone. Just a minute. Good afternoon, everyone. Welcome to the live session one for the course of Mathematical Modeling of Manufacturing Process. My name is Devanjan, and I am a PMRF research scholar at IIT Kharagpur in the Department of Mechanical Engineering. I will be acting as an external TA for this course, and I will try to have some problem solving sessions throughout the duration. So now I would like to mention here that this session is solely arranged to do some problem solving which may help you to do your assignments for the course. So during the session, I will not discuss about each and every details of the topics covered during the week, but yes, we'll discuss only the problem related concepts during the discussion. I may try to cover most of the concepts again, what you have gone through or what you have learned during that week from video lectures, right? So let's start. Uh, can you take some few times to solve this question? You need to just match the two columns, and can you take some time and tell me the answer?
Sorry, your screen isn't visible.
Sorry,
Your screen isn't visible, sir.
my screen is visible, right?
No, sir, your presentation is not visible.
Yeah. So here basically I have tried to explore on the different properties of the material which you have gone through your in the first lecture. So there are ferrous alloys, there are non-ferrous alloys, there are high temperature resistance material, there are polymers, there are smart materials also. So please recall those concepts and can you please tell me the answer?
Sir, the screen is not visible, sir.
Screen is not visible. Okay, wait. Is it visible now?
Yeah, yes, sir.
Yeah. Can you tell me what property a superalloy can have, or few names of the superalloys?
Sir, Incon is one.
N colon, right? Anything more? Yeah. So Inconel is a nickel-based
Hesloy.
alloy. Hastelloy, yeah. So Hastelloy, Inconel, these are few superalloys. So basically, a superalloy is an alloy which can have the ability to operate at high temperature, right? So they have excellent strength to creep deformation at that elevated temperature. Uh, These strength can be formed because of solid solution strengthening or precipitate strengthening. Are you aware of this substitutional solution or interstitial solution from your material science course?
Sir, yes.
Yeah. So basically, in substitutional solution, so say, just let me go through. Yeah. Say these are your atoms. So this is your hub plane. Okay. This is your slip plane basically. So the deformation is basically of this displacement of this slip throughout the system. So in substitutional solid solution, atoms of solute can replace the atoms of solvent. Since the size of the solute and solvent are different, uh, the dislocation movement can be interrupted, right? Which can take high temperature or stress level to move it through the system. So basically, you need to move the sleep plane to have the deformation, right? So because of this substitutional solution, it will impedes that movement of the sleep plane. So that's why it can sustain so much of high temperature. Now in interstitial solutions also, basically this is your solute atom. For substitutional solid solution, now for interstitial solid solution, this will be smaller in size compared to the solvent, right? So here the solute atoms are small enough to fit into that solvent atoms. But again, yes, these atoms also can impede the movement of the dislocation, and because of that impeding the dislocation movement, it will go up to very high stress level. So much of hard can sustain so much of temperature. Now can you yeah Now can you tell me of what can be the difference of thermoplastic and thermosetting polymer? So basically, this super alloy is matching with this one, can sustain high temperature, right? Now what about this thermosetting polymer and thermoplastic polymer?
Thermoplastic, they soft over a wide range of temperature.
Right. And for thermosetting,
Recycling not possible.
correct. So basically, this thermoplastics can have some high molecular weight. The polymer chains are associated by these intermolecular forces, which can weaken rapidly with increase in temperature and can form some viscous liquid kind of thing. So in this state, thermoplastics can be reshaped and are used to produce parts by some processing techniques. Can you tell me few of the processing techniques which can form some thermoplastic parts? Have you heard about injection molding?
Yes.
Yeah. So injection molding or compression molding are few of the techniques which are used to reshape this viscous kind of thermoplastic. Now in thermosetting polymer, it is kind of irreversible chemical bond during the curing process. So thermosets do not melt when it is heated, but yes, typically it can be decomposed but cannot be reformed upon cooling, right? So yeah, thermoplastic polymer is soft over a wide range of temperature, and for thermosetting, recycling is not possible. And I think for copper alloy, you're well aware of this thing, that this can be this is having some property of high electrical conductivity. Now, can you differentiate between steel and cast iron?
Steel is having less than 2% carbon.
Yes. So
Cast
3 is
iron
to F
having
and 7 is to B. I think in the first lecture video, professor has went through how steel and cast iron are formed, right? So basically, the raw material is of iron ores. So in the iron ores, there can be iron oxide and impurities also. So basically, chemical reducing reaction are used to extract the metallic iron. And so when you heat up the iron ore, you mix it up with limestone, coke, and air to have the reaction in the furnace, and in that way oxides are reduced. But mm, but the other elements like manganese, phosphorus, silicon, wet. Pardon me, huh? Someone is here. Is my screen visible?
Yes.
Okay. So yeah, what I was telling is, there can be some few more components like manganese, phosphorus, silicon, sulfur. These things can be added. So basically, they are extracted in the form of pig iron, and pig iron is cast into different shapes. Now, for steel, it is made by oxidation process, which decreases the amount of carbon. So basically, I think you are well aware of this Fe3C phase diagram, right? So if you go through this Fe3C phase diagram, you can see there that for the steel material, the carbon percentage is very much below of 2%. For cast iron, it is the carbon percent is higher enough. Uh, Now, for the smart material, there is only one option is remaining. So it will be variable stiffness through some external stimuli. So basically, in the smart materials, they are kind of engineered materials where they exhibit one or more properties which can be significantly changed into a controlled fashion by external stimuli such as stress. It can be moisture. It can be electric or magnetic field or temperature also. Let's not go into the detail, but yes, you can study always. The kind of properties they exhibit are really fascinating. So yeah, question one is over. I've also given the answers here also. Now in question two, can you tell me what is the atomic packing factor of ACP system? First, can you tell me what is atomic packing factor? So atomic packing factor or packing efficiency, packing fraction, these all are same. Can you define atomic packing factor? Here I have taken the HCP system because I felt this is most difficult thing compared to FCC and BCC. Obviously, you can follow any kind of basic material science book. So yeah, can you please define what is atomic packing factor?
Sir, it is the volume of its total volume that is occupied by the atoms divided by the volume of the unit cell.
Uh, can you make it a little bit louder? Yeah, someone of you were telling something. Okay, fine. So basically, atomic packing factor can be defined as say, this is your say number of atoms into volume of a single atom divided by volume of the unit cell, right? So in hexagonal closed pack system, if you see this crystal structure, so you have this A length and B length are similar because this is in the same plane, and you have the height of the hexagon as C as defined. And if you see in the reality, these atoms are the atoms are touching all together. So basically, A can be defined as 2R. Now, can you tell me what is the number of atoms? Means it's basically the equivalent number of atoms in the equivalent number of atoms in the unit cell. So, what is equivalent number of atoms in the unit cell for HCP crystal structure? You can refer this image. Basically, one corner atom. If you see this corner atom, this corner atom is shared by 6 unit cells, and this atom. So here one is in the top and one is at the bottom. The middle atom is shared by 2 unit cell. Now can you tell me what is the equivalent number of atoms?
6.
6. Right. How is it coming? So it's basically total 12. This 1, 2, 3, 4, 5, 6. So 1 by 6 into 12. These are 2 at the top and bottom, and you have this symmetry plane here. So you have total 6 equivalent number of atoms. Now what will be the packing factor? So it's basically 6 into what is the volume of unit cell? This is 4/3 pi r cube, and this is volume of the unit cell, right? So what is the volume of that unit cell? So it's basically 6 into 4/3 pi r cube divided by this area of the base, this base, this into the height, right? Now what is the area of the base? This area is basically can be, just wait. Yeah. Can you tell me what is the area of the base? This base can be decomposed into 6 equilateral triangles. Is it not the area? So the volume is, are you getting it? So the volume is 6 into root 3 by 4 into a square into the height. Now what you need to do, you need to get some, you need to get some relation between C and A, right? Are you getting it?
Yes, sir.
Yeah. Okay. So I'm removing this part. Now if you see the this symmetry plane in the middle plane, sorry, here it was one atom, here it was one atom, here it was one atom. These all are having length of A because these are touching each other. And in the top you have this atom I'm talking about, and see, this is A, this is A, this is A, this is also A because this top and this atom is touching, right? So everything is going to be of length of A. Now this Z axis, the length, the C, the Z axis is passing through the middle of this plane. Say this is your middle. Now can you tell me what is this length X? Is it not C by 2? It's the middle, right?
Yes.
Hmm. Now, so this is all about geometry basically. So this will be a right angle. Can you imagine this? Why this will be a right angle? It's basically the axis passing through the symmetry plane. Now assume this triangle, right? So square equal to x square. Sorry. So basically assume OB is of y. Up to this is okay for you? Sorry, just again wait. Yeah, up to this point is okay for you?
Yes, sir.
Okay. Now if you imagine this symmetry plane, so say this is your equilateral triangle, this is your equilateral triangle, this is your midpoint. So through this midpoint, this was your point O, right? This was your point B, this was your point C, this was point A. Can you tell me what will be this angle?
30.
Sorry,
30, sir.
30, right? So this was your Y and this was your A by 2. So all these lines which are intersecting this triangle perpendicularly, these are intersecting it at A by 2, A by 2, A by 2, A by 2. This is also A by 2, this is also A by 2. So Y is basically, sorry, just a minute. Now this is your one relation, this is your another relation. Now from here, can you tell me what is the C by A ratio? From these two relation? Just give me a quick number. Having calculator nearby you? Anyone is having any answer? Okay, from these two relation you will get some C by A ratio, yes or no?
Yes, sir.
Right? So say this will be something. I am also not sure what it will be. I am trying to just explain the things. Okay, so you will get some value here, C by A ratio. So what was the packing factor? It was basically 6 into 4/3 pi r cube divided by 6 into root 3 by 4 into a square into C. So you have the C by A ratio, and also you know A equal to 2R. So from this I hope you will get the answer as 0.74 as atomic packing factor of HCP crystal structure. So please make sure that you are getting 0.74 through this derivation. Have you got this derivation?
Yes, sir.
Good. So here I have basically tried to make you understand that what are different properties of metal, polymers, and ceramics from the atomic structure point of view. Can you tell me here? Metals are having which bond, ceramics are having which bond, and polymers are having what kind of structure?
Metals covalent bond.
Metals base actually they,
Metallic bonding with large
they follow
atomic
metallic
masses.
bond.
They must form covalent bondings.
So in metallic structure, the metal ions are arranged, you can say side by side in a regular repeating pattern. The free floating electrons can act like a glue and hold the structure in place. So the sea of electrons are the main reason to conduct the heat or electricity, right? Whereas in ceramics, it's mostly covalent bonding, where it involves sharing of electrons to form the electron pairs between atoms. So because of this sharing things, because of this electron sharing and stable configuration of the atom, there will be no other electrons which will be remain to conduct that heat and electricity, right? So mostly ceramics are, so basically ceramic heat conduction, metal heat conduction, and also ceramics are basically used as insulating material, even for electrical also, right? Can you comment on the density of metal, ceramics, and polymers? Which one will be higher?
Density of metals greater than that of ceramics, which is greater than that of polymers.
Why polymers having so low density? Because of their amorphous morphology. So they are so loosely packed, the bond strength is so low. So you can understand this better. Like you can think of a polymer chain as a piece of spaghetti. A piece of uncooked spaghetti can form some kind of chain, but when you cook it and boil it in water, the chain softens and become capable of some complex folding kind of thing. So in amorphous structure, basically they do not have some crystalline formation. So it's basically all in a haphazard way, like this. They do not have any structure, proper structure, some arranged structure. Got my point? You have got my point, right?
Sir, can you please once again explain, sir?
For polymer one,
polymer. And also, I have a doubt, sir.
Yeah.
Like for ceramics, even ceramics have an amorphous structure. For example, glass. Glass is also a ceramic, and it is amorphous in terms of the structure also. So,
Yeah, means
so polymers have covalent bonding because they're bound from they are originated from the covalent bonding between the carbon, the other hydrogen, and other atoms. So
so these hydrogen bonds are or van der Waals bonds. These are, I think, mostly weak bonds compared to this covalent or metallic or ionic bond. A van der Waals bond is very much weak, I think. Even the hydrogen bonds also. Yeah, most of the ceramics, if you see they follow this covalent bonding, but yes, for glass thing, yeah, they are kind of amorphous structure. So means if you see in generalized view, then most of the ceramics can follow this covalent or ionic kind of bonding compared to metals which are having metallic bond. And polymers can, there are polymers also which can follow some crystalline structures also, but yes, for most, maybe for thermoplastics, actually, they can follow this amorphous structure.
is- so what kind of bonding can we say about polymers present in the polymers? Because there also we will find covalent bonds also, or anything
Yeah, they
specific.
can have covalent bond, also maybe there can be van der Waals force, which is a secondary bonding basically. I'm not sure, but yeah, you can go through the polymer bonding. I hope this, there is some H2 bond also, hydrogen bonding. So these bond strength are weaker than metallic and covalent bonding.
Okay.
So here I have tried to look upon few of the properties which you can think of. Yeah, there can be elasticity, there can be plasticity, creep, fatigue, which professor has gone through. So can you match the followings here?
Creep, slow, permanent deformation at constant stress level. C. Fatigue, cyclic loading. Latent heat, phase transformation.
Exactly. So if you see the metal creep properties, they basically occurs at temperature higher than some zero point 0.3 to zero point 0.4 of melting temperature. So basically, when you enter into the tertiary region failure, the failure will, of course, it will happen rapidly. At lower temperature, the strain increases with time. Maybe it can follow some power law hardening. Maybe in this region, so in primary creep region, strain can follow some power law relation with time. In the secondary region, it's a linear relationship. So strain is basically some proportionality factor into time. So as it is linear, the strain rate will be constant here. So it's almost constant because it follows a linear relationship with time, right? Now, in case of material fatigue, it is a phenomenon where the structures fail when subjected to a cyclic load. So this type of damage may occur even when the experienced stress range is far below the material strength. During a large number of cycles, the damage develops on initially it develops as some microscopic level, and then it grows until some macroscopic crack is formed. The macroscopic crack grows for each cycle until it reaches a critical length. Then the cracked component breaks because it can't sustain the peak load no longer, right? So because of that cyclic loading, so there will be this kind of loading. The fatigue will happen in the material. And yes, of course, for phase transformation, the latent heat is important. Can you solve the question for me? Just take your time and tell me what will be the answer. You are aware of this figure, right? Are you aware of this figure? It's basically tells about the yielding begins on a slip system when the shear stress of the system reaches a critical value, independent of tensile stress or any other normal stress on the lattice plane. So it tells about there is some uniaxial loading of 100 Newton. So here basically F is 100 Newton. You can you can assume cross sectional area of 20 mm square. Now it tells that angle between loading and slip direction is 30°. So this is your loading direction. This is your slip direction. This is 30. This is normal to slip plane. Now can you tell me what will be the resolved shear stress? Okay, tell me about the area of the slip plane. If this is your original cross sectional area, what will be the area of this?
A cos 30.
Sorry.
A cos 30.
Am I right?
Yes.
Is it okay? So it's basically the decomposition into two different directions. You can decompose the area, you can decompose the force also. So if you decompose the force in the slip direction, it will be F cos lambda, right?
Yes, sir.
So what will be the shear stress here? Right? So if you are you getting it?
Yes, I'm getting it, sir.
Yes, sir. Yes, sir.
Yeah. So if you calculate this, so maybe I found it something around 2 megapascal. I'm not still remembered. So it was basically less than the yield strength what provided. So it is not crossing the
Correct,
yield
sir.
strength. Sorry.
Correct, sir. Correct, sir. It's 2
Yeah.
megapascals.
Yeah. So if it is not crossing the yield strength, so the material will not be yield. So this law is basically a constitutive model for a single crystal from which you can tell about some constitutive model that when the material will be yielding or it will not be yielding, right?
Yes, sir.
Yeah. Can you shed some light on this? Which of the following manufacturing processes are dependent on strain rate predominantly?
Deep drawing.
You think deep drawing is dependent on strain rate? So when strain rate comes into picture, strain rate basically, what should I say? Strain rate basically comes into picture when the processors are very dynamic in nature. There can be anything. The inertial effect of the materials matter very much. So in these cases, strain rate plays an important role. So can you tell me what is means in these four techniques? What are the two processes, or what are the processes which are dynamic kind of thing? So whenever basically there will be a frequent change in mode of loading or magnitude level of the load changes frequently, or huge amount of load is acting at some short duration of time, during that time strain rate plays a crucial role. Are you aware of friction stir welding? What happens in friction stir welding or impact welding? These two are basically, you can tell them something like quasi static process. It is not at all dynamic in nature. So for quasi static process, stress is only a function of strain. Here strain rate does not come into picture. But whenever you talk about some friction stir welding or something like car crashing or something like impact welding, the processes are so dynamic in nature. So at that time you have to have considered the effect of strain rate and temperature to predict the stress very accurately. So basically in friction stir welding it is performed with a rotating cylindrical tool which has some profiled pin having dia smaller than the shoulder. So this is your pin and this is your shoulder. So this is your D shoulder and this is your D pin. So the heat is generated because of the rotation of the tool over the material. So there will be so much of heat generation because of that friction between the tool and uh, top sheet surface, and because of the plunging action of the tool also. So you have the rotation of the tool and also some pressure generation due to the tool over this surface. So there will be a stirring action of the material will get stirred and it will mechanically intermixes, diffusion will happen, so many things are happening at a single time. So during these times strain rate comes into picture to predict the stress accurately. Now in for the impact welding case also, in high velocity impact welding, it is characterized by low welding temperature and very fast welding speed. So the process is conducted at room temperature and no external heat input is applied during the welding. And when the transient force is applied on the external surface of the flyer, so this is your flyer and this is your target material. So when the flyer collides with the target, a jet of contaminants or oxide layers and even a thin layer of metal forms. So as a result, these clean metals, so when there will be no oxides, these clean metals are exposed to each other and the atoms are brought within their atomic distance and they form some strong bond. So if you see this zone, the velocity is something like 100 meter per second. This is so high that maybe in kind of microsecond. The bonding happens at low temperature. So you can see these kind of profiles here. This material will get sheared and bond together with this flyer material. So basically I wanted to talk that so whenever there will be some frequent change in mode of loading, or there will be a huge impact in short duration of time, even you think of some car crashing thing. So whenever the process is dynamic in nature, the strain rate plays a crucial role. So for this, friction stir welding and impact welding are dependent on strain rate predominantly. Uh, you got my point in this question?
Yes, sir.
Yeah.
Yes.
This is a very simple question. Can you work on that? So it tells about fracture load is 200 Newton. A original is 10 mm square. This is I am mentioning at instantaneous. What is this? 2% reduction of cross sectional area. Right? So what will be the engineered fracture strength of the material, and what will be the true fracture strength? Can you tell me what why this true stress strain curve is kind of increasing in nature rather decreasing, what you can see in engineering stress strain curve? Anyone?
So because after making it becomes weaker.
Yes, of course it will be weak. So say this was your, let us think from mathematical point of view. If it was original, so depending upon some plastic deformation or this uniaxial loading, this area starts to decrease a little bit. So during necking, it's you can get some cup cone kind of failure. So basically, when the necking happens, your instantaneous cross sectional area reduces from the original one. So if your area reduces, sigma will get increased, right?
Yes, sir.
Can you give me some answer here? Sorry, it was 10 mm square, right?
Seconds.
Is it okay? Am I right or wrong?
Sir, AI is equal to A naught minus 0 to A naught. We have A naught is equal to 10 now, sir.
A naught is 10. Yeah.
10 minus point 2.
Huh. Now, can you tell me when can you when can you define a material as a ductile material and as a brittle material? Means from which property you can tell that material is ductile and material is brittle?
Yielding.
Sorry, yielding.
Yielding.
Yeah. So yielding is one. Anything on
From
strain
fractures.
part? You can see the elongation of the material also, the strain it sustains. So if the elongation, in general, people says that if the elongation is more than 5%, the material can be called as ductile. If it is less than 5%, it can be called as brittle. I think you have gone through the concepts of strain hardening. You know about strain hardening, right?
Yes, sir.
Yeah. So let us not go through everything of this stress strain curve. So these are very basic things. Yeah. This is my last question. This is very simple. Can you tell me?
For force measurement, we use load cell.
For force measurement, we use load cell, right?
Pressure measurement, thermocouple.
Temperature measurement, thermocouple.
Microfarners, Vickers.
Right. Are you aware of this ACM or XRD thing?
Sir, ACM is scanning electron microscope.
Mm-hmm. What happened to my pen? XRD is basically some X-ray diffraction technology from which diffraction, right? From which you can identify the phases. So if you see this binary phase diagram, there will be some phase formation when there will be a compound formation, phase formation. You can see when two materials are mixes together. So you can identify which phases has exactly been formed in the say if you are joining say Fe to aluminium or say copper to aluminium. So for copper to aluminium, if you see the phase diagram, there will be phases like aluminium rich phase, there will be phases like copper rich phase. So these kind of phases you can identify through XRD, and from EDS you can identify the exact composition of this compound, the atomic percentage or say weight percentage. Say this is your copper material. copper based material, aluminum based material. So bonding, whenever bonding can happen, there will be some diffusion zone. Because of this intermetallic formation, they will bond together. So at different location of this place, you can identify what will be the atomic percentage. Say this is your point A. So in point A, you identify how much copper is there, how much aluminum is there. So these are typically used uh, to characterize a material, right? So here I want to stress upon the residual stress measurement thing. Am I audible, right?
Yes, sir.
Yeah.
You're
So,
audible.
can you tell me what is residual stress?
It's remaining in the material after some machining or manufacturing process.
Hmm, hmm, hmm. So basically, residual stress is generated when an object is stressed beyond its elastic limit, resulting in some plastic deformation. So, say you have heating up to uh, up to some melting temperature, not melting, maybe it can be nearby to melting, and the object is cooled from a higher temperature. So whenever there will be a large difference in the rate of cooling throughout the body, so because of that difference in cooling rate, it results in some uh, localized uh, localized thermal conduction, and there will be some thermal gradient will be there. So depending on this thermal expansion coefficient, so at different location of the material, they experience different kind of stresses. It can be tensile, it can be compressive, right? So residual stress is also important during this phase transformation part also. So during phase transformation also, there can be a volume difference between the newly formed phase and the surrounding material, which is yet to undergo the phase transformation. So at that time, residual stress plays a crucial role. Uh, have you heard of this Borschinger effect thing? What is Borschinger effect? Yes or no?
No, sir.
Hmm? Can you tell me which one will be higher, this tensile strength or compressive strength? First, please tell me, you are aware of Borschinger effect or not?
No, sir.
No. Okay, fine. So basically, this Borschinger effect refers to a property of materials where the material's stress strain characteristics change as a result of this microscopic stress distribution of the material. So if you talks about this residual stress, there will be somewhere tensile stress, there will be somewhere compressive stress. So for example, for Borschinger effect tells about there can be an increase in tensile yield strength occurs at the expense of some compressive yield strength. So basically, if you are subjecting the material to tension, you can get some tensile yield strength. And again, when the material is subjected to some compression, from Borschinger effect, it talks about this compressive strength will be lower than the tensile one. It is a general phenomenon found in most polycrystalline metals. So maybe I should not go into that detail. It will not help you in this situation. So you can remember it like that for modeling of residual stress. Boschninger effect plays an important role. You can study about this. Let us not go into detail in this session. Maybe professor will go through these things. Okay, so it's done from my side. I think you'll get these videos and presentations from NPTEL team. Any question from your side?
No, sir, it's clear.
Okay. Anyone? Okay. So let us stop the session here. We'll meet again on next Sunday.
Yes, sir.
Okay. Thank you.
Thank you so much for the session, sir.
Thank
Thank
you.
you. Thank you.
Have a good day.